Very few of the pioneers in the search for the atom were actually looking for ultimate smallness. Nevertheless, 25 centuries of curiosity about the basic nature of matter gradually produced a mosaic of scholarly ideas and observations, which led to the work of this man, the English chemist John Dalton. Dalton fell backwards through the door, which led to his chemical atomic theory. He was actually looking for an answer to why water absorbs more of one kind of gas and less of another. He decided that when water absorbs a gas, particles of the gas must fit into spaces or pores between particles of the water. Why does water absorb more of one kind of gas and less of another? Dalton thought some kinds of gas particles were lighter, so relatively few would squeeze between the water particles. While with another kind of gas, heavier particles would sink in greater numbers between the pores in the water. Dalton's theories implied that matter was made up of individual particles with spaces between them. Dalton concluded that elements of matter consist of characteristic kinds of particles. The particles or atoms of an element are identical to each other. Atoms are indivisible. There are as many kinds of atoms as there are elements. The atoms of one element cannot be converted into the atoms of another element. Atoms in chemical reactions are neither created nor destroyed, merely rearranged. Dalton's ideas suggested a way of explaining an earlier observation, Prost's law of definite proportions. If each element is a particular kind of atom, then these atoms combine in fixed numbers to form what Dalton called compound atoms. Dalton extended this thinking into his law of multiple proportions, which described how different compound atoms can be formed by two basic elements. The simplest possible formula is one atom of each kind. Next simplest is one of one kind and two of another. After Dalton, the pace of discovery quickened. Michael Faraday used electricity to decompose water into hydrogen and oxygen. He decided that electricity was the force of affinity that held compounds together. Faraday did not agree with Dalton's theories about atoms. Nevertheless, he had found the glue which held Dalton's atoms together. In another experiment, Faraday began with a sparking apparatus, to which he connected a glass tube. When he partially evacuated the air from the tube, he saw pink streamers of light flowing between the terminals. Over the years, techniques for reducing pressure in the discharge tube improved. The pattern of light in the tube changed as pressure was reduced, until finally, in a near vacuum, an eerie green glow illuminated the tube. William Crookes designed more complex vacuum tubes and showed that whatever caused the glow seemed to stream from the cathode or negative terminal. By interrupting this stream from the cathode, he showed that it traveled in straight lines. The stream also caused an increase in temperature of objects in its path. And it also produced a mechanical force, a push. Crookes guessed that these so-called cathode rays were in fact a stream of particles. In 1897, J.J. Thomson designed a specialized cathode ray tube. A cathode ray particle leaves the cathode and travels between charged diaphragms to focus the rays in a straight line to strike a fluorescent screen. Charged plates, either side of the tube, could deflect the cathode ray towards the positive plate, which persuaded Thomson that cathode rays consisted of negatively charged particles. Electromagnets could also bend the cathode rays. By balancing the deflection caused by the magnetic field with that caused by the electric field, he was able to calculate the charge to mass ratio of the particle. Cathode terminals made of different metals had no effect on this ratio. Nor did traces of different gases in the near vacuum. It appeared that these cathode ray particles, rechristened electrons, were a fundamental particle of all matter. Was this an indication that ultimate smallness, the atom, is composed of something still smaller? In 1907, R.A. Millikan established that all electrons are identical by determining their minimum charge. Millikan used microscopic droplets of oil falling from a pinhole. He calculated the rate of fall due to gravity alone, then applied a known electrical charge on plates above and below the droplet. The resulting electric field would influence the rate of fall because the oil droplet carries a charge. One way to change the charge on the oil droplet, liberating electrons. Every time a free electron attached itself to the droplet, the charge changed, and in turn, the rate of fall changed. Over thousands of experiments, Millikan found the smallest single discrete rate of change and decided that it represented the charge of a single electron. But how could an electron consistently have a basic charge and yet be a part of matter, which normally has no charge? A model of the atom which includes electrons must somehow neutralize them. J.J. Thomson provided the first such model, what became known as the raisin-bun model of the atom. He proposed that an atom was a positively charged dough with many negative raisins embedded throughout. The ones, by the tens, or at most about 100. 1,000 electron buns were too rich for scientific tastes. But back in the kitchen, another cook was soon to prepare a more satisfying model.